we have a differential equation here. Now that differential equation represents what happens if we got water in this bottle and allowed to exit through this tube here. Okay? Now the reason the differential equation is what it is related to the physics. We don't have to know the physics to understand this, but since most differential equation students are also physics students, or were or will be, and will be applying differential equations to physics, I'll just mention the physics. Okay, the physics is simple. Water exits here with some velocity. The rate at which the water descends here, by simple geometry of cylinders, assuming that we're in the cylindrical part of this container, is in a proportion that's determined by the cross-sectional area of this tube and the cross-sectional area of the cylinder. So, for example, if the cylinder has 100 times the cross-sectional area of the tube, the rate at which water is going to decrease here is 1/100th the rate, the velocity of the water flowing through the tube. Very simple. Now, that's not even physics, that's just simple geometry. And of course you have to assume that water is incompressible, but everybody by this point should know that, and if you don't, make note of it. Okay? Not totally incompressible, look it up in the tables. Okay? But very, very close to incompressible. Now, the physics of the situation is pretty simple. When you lose water up here, the potential energy of the system changes by the potential energy of the water up here relative to here. And that comes out as the kinetic energy of the outflowing water. Now, the kinetic energy is proportional to the square velocity. Okay? So the velocity is proportional to the square root of the potential energy change, which is just proportional to the depth, so that the velocity of the outgoing water has to be proportional to the square root of the depth. For an ideal fluid, and for water, there are compensating factors that make this system act very much like, to at least 3 or 4 significant figures, like an ideal fluid. Okay? The compensating factors reduce the effective density of the fluid. We don't go into all that. We don't need to for differential equations course. Just seeing how the differential equation applies and understanding that conservation of energy tells you this. Okay? Now we want to solve this differential equation. And of course I threw this out second day of the class and said solve it. Okay? Now in the last class we looked at a separable equation. The very first thing we did, we solved a separable equation. So it would be reasonable, but that was only 2 days ago. Who's had time to digest anything? Okay? And apparently didn't get to that in homework. But the separable equation means you put all the y's on one side, all the t's on the other. And for reasons that we're not going to detail right now, you can treat dt as just an algebraic quantity that you can multiply on both sides. So you can rearrange the equation to this, and then you can integrate both sides. And I didn't bother putting the integral signs in, but I'll go ahead and do that now. Okay, so we integrate this, and we integrate this. I'll leave the negative sign outside the integral, you know we can do that. Okay? And we get an antiderivative here, and we get an antiderivative here. I don't have to explain how we get those. And you get an integration constant. Now you get an integration constant on both sides, but the constants are totally arbitrary. So if I take whatever constant I got on this side and subtract it from whatever constant I got on this side, I still have a constant that's totally arbitrary. In other words, either constant can absorb the other, and we still have an arbitrary constant. So I just write the constant on this side. Then I solve for y. Divide both sides by 2 and square both sides. Okay? And now there's a question, why didn't I square the c? Because I don't want a c squared. It's because c could be any number at all, right? Okay? Actually, I didn't square the c, so I don't even know why I'm saying that.
You didn't divide it by 2.
Oh yeah, I didn't divide the c by 2, yeah. Duh. Okay, I didn't divide it by 2 because c is totally arbitrary, so c over 2 could still be anything at all, so it's still just an arbitrary constant. Okay? Now, then I just square this, okay? Then there's a question, well, why didn't I just write c here, because c squared would be an arbitrary constant, okay? Well, actually it wouldn't. It would be a positive constant, right? Whereas this is totally arbitrary. It could be negative. This would have to be positive. But why don't I just say, okay, just call this c and now say that c has to be positive, okay? Well, I could, and that'd be perfectly valid, except I got a c here, okay? So I can't make that an arbitrary or even a restricted constant, restricted to be non-negative. I said positive. It'd have to be non-negative. But since I've got a c here and a c squared here, and since this c can be negative, I can't just do that.
Why would c have to be positive?
Well, c is an arbitrary constant. If I replace c squared and just call this c, it can't be negative anymore.
Okay.
Okay? And then if I wanted to call this square root of c, well, you don't know whether I want to use the positive square root or the negative of the square root. Okay? So it complicates things. So keep things as simple as possible. That's the way we're going to write it. Okay? When we expand it. Okay, well, now we take a system like this, and we can put water in it to any depth we want, and we can mark where it is and time it, for a short time, and see how far it moves. And then we know the rate at which the depth changes, okay? Now what we might do, and it still wouldn't be totally accurate, except this being quadratic, it would be, and you don't have to worry about that. You time it over an interval, and then you say, well, at the midpoint of that interval, that's where the average rate is equal to the exact rate. Okay, so the next thing we do,
Yeah. Who's this?
we
Oh, yeah.
measure this, and we measure that depth, and then maybe we get something like this. Maybe y changes at a rate of negative 2 centimeters per second when y is 10 centimeters. Our depth would be 10 centimeters. We'd be going down at negative 0.2 centimeters per second. Okay? And I say that, because I'm using vernacular here, but and that 10 centimeters is the depth when t equals 0, which would have been a better way to state that, but trying to make you think a little bit. Okay? Then I wrote something down that's inconsistent with this, so I crossed it out. Okay. So we take this information. Now what can we do with this information? Well, this is a rate, okay? That's a dy dt. So dy dt would be negative 0.2 centimeters per second. That's the rate of change of depth with respect to clock time. That's what dy dt is, and that's what this is. And then that occurs when y is 10 centimeters, so plugging these in, I can easily evaluate k. I get k equals this, and then I approximated it. Square root of 10 is about 3, 2/3 is about 0.67. So I said, okay, about 0.07 down here, but actually it's closer to 3.1. It's a little more than 3.1. And that brings it down to what I thought was going to be 0.064, and then somebody used a calculator, which you need to check out since it was not consistent with what I said, and told me, yeah, it's actually 0.063. Okay, well, I'll accept that, right? So I made some corrections where I was using 0.07, I used a 0.063, okay? Actually, if we're doing this with water, this model is accurate enough that we would want to use at least 3 significant figures here, and we would get no significant or very small significant discrepancy between theory and practice, okay? Given that all this stuff is observed to 3 significant figures, we should be pretty much right on to 3 significant figures with any prediction we make. Now it'd be difficult to have enough instrumentation, and also we'd want a rigid cylinder because that can expand just a little bit, and that would throw things off, and that's an interesting problem, that leads to another interesting differential equation. We'd have to modify this equation if the cylinder expanded or contracted for different depths. Okay? And then, it bulges, so it's not even a uniform contraction. That would be very interesting. Give us a differential equation that if we take it and consider every possible nuance of what would happen with this system that could affect our results, we'll end up with a differential equation we can't solve. But it's not going to be much different than this. Okay? So there are things we can do with approximation since we already have a solution for what we would call the first order effect, the dominant effect, which is this. So even if we take account of things like that and even thermal expansion that might change, okay, if the water's at a different temperature than the air, all kinds of stuff that you would have to take into account. You could incorporate that into your differential equation. But we're in the second day of the course. We don't even have a clue. I don't know. I could speculate on the nature of that differential equation, and I suspect it's not solvable except numerically. Maybe though, I haven't written it out. Okay, and of course there are techniques that I might not be aware of. There's certainly techniques that I'm not aware of. Okay, anyhow, so we have this. Then we have y of 0 is 10 centimeters because the 10 centimeters occurs when t equals 0, right? We call this an initial condition. Now the question came up, well, aren't there two initial conditions? Isn't this an initial condition? No. Initial conditions apply to the solution. Okay? This is just a parameter of the problem. Okay? And it's kind of a fine distinction at this point, but there's only one initial condition. And for a first order differential equation, you can only have one condition on it because you only get one arbitrary constant. You can adjust this constant to fit the condition. Okay? So let me just make a note here, first order equation. Now what do I mean by first order equation?
Only one derivative is being taken?
Yeah, only the first derivative. Okay? So, first order equation with only first derivative, we can fit the solution to one condition. Doesn't have to be an initial condition. I could have said that y equals 10 centimeters when t equals 40, right? 40 seconds, because I'd want to specify my units on that.
Would you still call it an initial condition?
No, you'd call that a given condition. You might even call it a boundary condition, but that's not a boundary, so you wouldn't. Let's not worry about the terminology. You can fit one condition. So, you can see how that would work. Say y of 0 is 10 centimeters. Well, y of t is this, as we figured out here. I use this form rather than this because it's simpler. Then we'll expand it. Okay? Well, that means that y of 0 is whatever this is when t equals 0. Well, if t equals 0, you get 0 here, so you just get c squared. So y of 0 is c squared, and y of 0 is 10 centimeters. Okay? Now, if it's y of 40 equals 10 centimeters, then we'd have to have 40 seconds here, right? The seconds would take care of the seconds there, so we'd still have consistent units, okay? But, yeah, then this expression would be, a little more, not really any more complicated. It wouldn't be a nice round number like 10, but we could still figure it out, right? Also, whatever c is, that is y of 0, right? So if y of 40 was 10 centimeters, well, 40 times 0.063 is like 2.4. You're going to hold me, it's 2.52. Divide that by 2, it's 1.26. Okay? That can't be right. 40. That is right. Okay, so c squared would be like only 11.26 centimeters. C wouldn't vary much by that. And I just don't believe it, but maybe, because that's maybe kind of a slow descent. Okay? Anyhow, that was a digression. You can go back and analyze it if you wish.
Wouldn't you have to expand that quadratic?
No, because if you plug t in here, you get a definite number here that's added to c. Right?
Yeah.
And that should equal 10. So c should be, and I said it should be the square root of 11.26, it should be 9.74. 8.74. Can't do arithmetic. Okay? Because that would decrease the value of c, right? But don't need to worry about that. Actually, it has to increase. Yeah, it's negative, never mind, it increases the value of c. It would have to increase it because y of 0 would have to be more than 10 centimeters. If it was at 40 centimeters after 10 centimeters after 40 seconds, it had to start higher, right? Turns out it doesn't have to start all that much higher, which means it's going to go down pretty slow over tens of minutes. You can conclude that, especially if you can do a little arithmetic in your head, which I can still do, but I can still get it backwards. Okay? So you can't rely on it. I'm saying this will change over tens of minutes. Okay? I don't think it'll take an hour, but maybe. No, it won't take that long. Okay. So anyhow, there we've got it. So the point is, again, we solve the equation. We have some conditions that allow us to evaluate k. So now we know what k is, and we can take our initial condition, whatever given condition, even if it was y of 40 equals 10 centimeters, okay, and evaluate c. And then we have our function. And I'm claiming if you do this under controlled conditions with a rigid cylinder, this is going to work very accurately. The first time I did this was back in the days when we had DOS computers that gave us really tiny pixels. And I did a curve fit to the data that I got, and every pixel disappeared in the curve. And the curve was really thin, not like the big old fat things that Windows wants to give you. Okay? It was impressive. It blew my mind. It's one of the formative events of my middle age. Okay. If you have formative events in middle age. Okay? Anyhow, you get this function. Now, again, first order differential equation can fit one condition. Separable equation, easy to solve. And the equations I gave you to do for today that you didn't get to, but better get to by next time along with the ones I give you. Okay? Are equally easy to solve. You might have to go back and look at the videos. They're posted. But I think with common sense, because y'all are getting pretty good at applying common sense, you can solve. Okay? That's essentially the procedure. Now let's look at a more interesting example. Okay? Yeah, okay, I'm gonna cut this video. I want to talk about the textbook.